Welcome this afternoon to our talk on Android security. My name is Adrian. I work on Android security. Xiaowen will be joining us in just a minute as well. It's going to be a bit of a whirlwind tour. If I talk too fast or Xiaowen talks too fast, I apologize. But there's really been a lot going on in the world of security on Android and Google Play over the last year, the last 2 years, the last 5 years. And so we're going to try to touch on quite a bit of that as we go through here today and give you the information that you hopefully need and certainly seem to want. We've got a lot of people here today, pretty exciting. What we're going to cover is we'll talk a little bit about the security services and from there hand off and begin talking about the core operating system and app security. So we'll dive right in. Yesterday we heard mention of something new, exciting, Google Play Protect. What is Google Play Protect? The core of it is an engine that we've built over the last several years to protect all of the devices in the Android ecosystem. This slide has grown year after year, and now we talk about over 2 billion devices around the world that are protected by those services, scanning over 1 billion devices and checking over 50 billion devices and the applications every single day. So incredible scale. And the reason that we have that scale is because we need it to be able to see what's going on an ecosystem that's on a mass, really almost the majority of devices that are out there in the world. To be able to actually look at all of that data, of course, requires computational resources. Turns out Google has quite a few of those. We use just a tiny sliver of them to look at the data every day. Over 20,000 dedicated processors that are looking at that application data, analyzing it, diving deep into every single new application that we find, over 500,000 new applications discovered every day, and trying to understand how they behave in our environment, how they behave out there in the real world, and what risks they might pose for users. Now, the reason we do that, of course, is to protect users. And so one of the most important things that we do is try to keep an eye on what is the risk that users are being exposed to. Clearly, over the last few years, what we found is that users of Google Play are in a much safer position. They're about 95% safer if they're installing applications that come from Google Play. And the reason is we're able to use data that's gathered outside of Google Play and then analyze that in the context of an environment that's much more controlled. And so applications at the time that they're uploaded, we're able to analyze them, understand what's in there, and then make good guidance and provide that kind of guidance. But we also provide those protections outside of Google Play. And so that's what we wanted to show here, is that over the last few years, we've been carefully tracking this, keeping an eye on what's going on, and making sure that users are being protected. From my perspective, it's all about the graphs. But that's not really how most people think about security, because most people aren't looking at the entire ecosystem at once. What they want to know is, am I safe? And so that's really what the announcement was yesterday, putting really in a brand, understanding that these protections are there and making them more and more visible to users, but also that Google is standing behind this protection, right? It's saying Google is going to protect you on your Android device and make sure that we have the best protections in place throughout the devices. And so that's really what we're focusing on. How do we do that? We do that in a variety of different ways. We're investing in increasing the intelligence, the ability to analyze what's going on these devices, as well as what's going on inside of these applications, expanding the scope of the types of protections that we provide, and also, quite simply, switching from that graph mindset that I've latched onto in my life into the user mindset, where what they want to know is, am I being protected right now? Am I being protected? What it is that Google is doing to look out for me. And so we've got a lot that we're doing in terms of increasing user visibility. When I talk about that increased protection, one of the most important things that we've learned is that we can't do it all as humans, right? When you're talking about 500,000 new applications that are discovered and analyzed every single day, more and more we have to rely upon the intelligence of machines to be able to do that type of analysis. One of the largest areas that we've been investing in is what everybody refers to as machine learning or artificial intelligence. At its most sort of simplistic, what it is it's us working with the machines to train them, right? This is a picture of a clustering algorithm that's grouped different types of malware based on the behaviors that those applications exhibit out there in the world. And so when we're looking at 500,000 new applications every day, a clustering algorithm gives us the ability to quickly hone in on the ones that we think are highest risk. Those may be applications that are brand new, that no one has installed. Those may be applications that have been out there for a while that we're starting to see a change in their behavior, right? But the key is using these systems to understand and make those kinds of quick decisions so that a user doesn't have to make them, so that you as a developer don't have to make them either, and you don't have to guess, because you can rely upon the investments that we're making to analyze all those data points and help make those decisions for you and inform you about what's going on these devices. The other thing that we've begun to recognize is sometimes we just name things wrong. There's a feature that we released a couple of years ago called Android Device Manager. How many people had Android Device Manager installed? For this audience, it's about 20%. So you're about an order of magnitude higher than the overall user base in terms of percentage of people that had Android Device Manager installed. Not shocking, given who we are and how many of you are Googlers? No? OK. Find My Device, a simple way to take an existing set of technology, expose it to users, and make it easier for them to understand how it is that they can get to it. And of course, we've added new features, things like battery and Wi-Fi status, tracking the device in the background so that if it gets turned off, you know where it was before it was turned off. You don't have to do the query in real time. A number of sort of basic usability features to make sure that this functionality can be increasingly valuable for users. Because after all, the most significant security risk that the average person is exposed to is actually this one. It's losing their device, whether it's accidental or whether it's someone taking the device out of their possession. The other thing we wanted to do is just let people know that this was happening, right? The number of times that I've read the statement, Google doesn't look at the applications in Google Play, just blows my mind. Every single application that's uploaded to Google Play goes through a very rigorous screening process, both at the time that the developer is enrolling to become a member of sort of Google Play publishing process, and at the time the application is published. And every single day after that, we reanalyze all of those applications. So it's absolutely a lot of that kind of intelligence that's going on in the background and analysis that's going on in the background that simply wasn't exposed. And so a lot of the work that we're doing right now is to just figure out how to delicately indicate to the user, whether that be a consumer or an enterprise, yeah, this is happening. We're checking these things, and we've got your back. But it's not just about consumers, right? It's also about application developers and making sure that they have the ability to leverage these services as well. Right now, Google Play Services is rolling out a new version, and one of the APIs that's exposed is what we refer to as the Verify Apps API. In the past, we've talked publicly about Verify Apps, which is the mechanism that's used to evaluate on a device and to check for a user on a device whether something is potentially harmful or a piece of malware. What we've done with the Verify Apps API is just made that available to any application on the device. So if you're concerned about whether or not your application should be running, you can check, are there any other apps on this device that I should be worried about? What are those applications? Let me know what they are, and so then you can evaluate whether or not you think it's an appropriate environment as the application developer for your application to continue to execute. That builds on other technologies that we've provided in the past. Last year at Google I/O, I referenced the SafetyNet Attestation API. This is an API that we use to evaluate, in the context of Google's understanding of a device, whether it is a certified, secure Android device. And we provide that literally as a signed statement, right? So you invoke the attestation API. It hits a round trip off of a Google server. We do an evaluation of the software integrity on that device, compare it to what we know about what that device should look like, and then make a statement back to you of, yep, this looks good, or no, it doesn't. Right? This is one of the critical pieces of technology that allows for delivery of, for example, Android Pay, where there's a requirement that this be a certified device and that it be operating in that kind of an environment. But it's an API that we've made available to any application that wants to take advantage of it. We're going to continue adding these kinds of technologies. reCAPTCHA was a technology introduced almost 10 years ago in the context of the web to do quick evaluation of whether or not the entity interacting with your web UI was actually a human. That's now being provided as a SafetyNet API as well. So in the context of your application, you can use a reCAPTCHA to evaluate whether or not there's automation of your application. Right? This is particularly valuable for what I think of as low-cost services that you want to continue to make available for free, but you want to cut down on the amount of abuse that's coming through bot farms and other types of automation. Right? Very valuable for large-scale web properties. One of the things that's come out of us being able to understand what's going on in the ecosystem is the ability to revisit some of the technologies that are actually baked into the core platform. Unknown sources was a flag that was introduced when Android was launched almost 8 years ago that gave the individual the ability to change where they wanted to install applications from. over the last few years, we've begun to understand what those install patterns look like. We've been able to analyze what the risks are that users are exposed to. We've certainly come to appreciate that Google Play is a safer place to install applications from, but we've also come to appreciate that there are many other safe places to install applications from as well. And so we want to simplify for the user the ability to install from those other safe places without introducing the risk of installing from just anywhere that's out there. So one of the changes that was introduced with Android O is a modification to how unknown sources works. So now it's on a per application basis. You decide, yep, that app store, it can install. But that doesn't mean everybody can install. And really that's targeted at making sure that apps are being installed from more trustworthy places where the user has delegated that kind of trust to the specific entity. So that's an example of the types of changes that we're making at the platform level. I've got Xiaowen here, I think is going to come on up and give you a little bit of insight into some of the other changes we're making to harden the operating system.
Thank you, Adrian. My name is Xiaowen. I'm the product manager for Android Platform Security. And today, in this next section of the talk, I'd like to give you an overview of the changes that we've made to the operating system to make it more secure, as well as to harden it. We've collected a lot of data on the impact and the adoption of some of these features. So I'm excited to share some of that with you. So let's dig in. We'll start with the basics. And that begins with verified boot. So verified boot is Android's secure boot mechanism, where we check the signature of every stage of boot before running it. And that has come a long way in the last few years. With Android Marshmallow, we started requiring verified boot for all compatible devices. With Android Nougat, that became verified boot is now strictly enforced, and that's required for all compatible devices. And now with Android O, we're providing guidance to our OEM ecosystem to add a couple more security enhancements to really round out the feature set of verified boot, starting with rollback protection. On compatible devices on Android O, verified boots will no longer boot an operating system that's known to have been rolled back to an older, potentially much more vulnerable version. Also, with verified boot, we have hardened the unlocking mechanism, the bootloader unlocking mechanism. And what that means is any bugs or any compromise in the Android operating system cannot unlock the bootloader. Only you, by interacting with the bootloader itself, can unlock the bootloader. So while verified boot protects your operating system, Android uses encryption to protect user data. And that has also come a long way in the last few years. As of Android Marshmallow, all compatible devices are now required to support encryption, and required to be enabled by default. As of Android Nougat, we added a major upgrade to the encryption story called file-based encryption, where we encrypt different storage areas with different keys. File-based encryption made the user experience of encryption much, much better without sacrificing security. As an app developer, in fact, if you're interested in running your app before the user first signs in, before the user first unlocks their device, check out our FBE documentation on our developer website. With Android O, we have continued to improve on FBE and added in a few more features, such as key ejection. So how are we doing with encryption? We looked into the data and see that over the last few years, encryption on Android, we've seen a significant adoption. While it's on Android Lollipop devices, encryption was very, very low. On Marshmallow, that jumped to about 25%. And now in Android Nougat, we're seeing encryption support at around 80%. As a matter of fact, we started requiring encryption on compatible devices as of Android Marshmallow. The reason that number didn't jump immediately to 100% is due to a couple of factors. One is a lot of Marshmallow devices were upgrades from Lollipop, and so those devices were not required to be encrypted when they first shipped. And also, because of the wide variety of devices that are supported by Android, we still see a lot of very low performance devices that are not yet capable of supporting encryption. Nevertheless, we could expect that number to continue to increase. And we see that encryption on Android is now the norm and no longer the exception. Another way in which we are protecting user data is to improve the secure lock screen experience. With Android Marshmallow, we introduced official support for fingerprint sensors. And that had a significant impact on the adoption rate of a secure lock screen. Also, we have been working with manufacturers to put in requirements to make the implementation of a secure lock screen much more secure over time. From the very beginning, fingerprint implementation, the fingerprint verification, was required to be implemented in secure hardware, such as the Trusted Execution Environment, the TEE. With Android Nougat, we started requiring that PIN pattern password verification also take place in secure hardware. And now with Android O, we're adding in support for tamper-resistant hardware. So similar to the chip that you see in credit cards today, Android now supports having that chip be embedded in the hardware and using that chip to do PIN pattern password verification. This significantly raises the bar, makes it much, much harder to perform a physical attack against the device to bypass the lock screen. So how are we doing with secure lock screen adoption? We see that that has also increased quite a bit over the last few years. Whereas on Lollipop devices, adoption was only about half and half. That increased to almost 70% now on new Android Nougat devices. And a lot of that was probably driven by the fact that a lot of new devices now have a fingerprint sensor. And we see from the data that fingerprint devices are much more likely to have a secure lock screen than across the entire Android device system, device market. The other thing is that we do see apps such as Android Pay and some enterprise apps require enabling a secure lock screen to function properly. So that might also have had an effect. As developers, you might want to consider really taking advantage of the lock screen and incorporating that into your own application. So we see a lot of banking apps, for example, incorporating fingerprint authentication. So while encryption and lock screen protects user data, Android has a robust permission model to give users control over app access to their data. And that has also improved quite a bit over the last few years. With Android Marshmallow, we introduced runtime permissions, and we've seen great adoption there. With Android Nougat and Android O, we are continuing to update the permissions model to make it more usable by good apps and less abusable by bad apps. So before we go into the details of that, let's check out how runtime permissions are doing. We looked into permission requests. And so for each request, for, let's say, the camera group of permissions, we see that about 65% of users, 65% of those requests are accepted by the users. So that's towards one end of the spectrum. Towards the other end of the spectrum, we see that for the phone group of permissions, only about 44% of the permission requests are accepted by the user. So users are actually very judicious in controlling which apps have access to what data. So I think there are a couple of takeaways here for apps. The big thing is, of course, to follow permissions best practices so you can really take advantage of runtime permissions and provide the best user experience. As an example, you should always make sure that users know why you're asking for a particular permission and be able to fail gracefully if they decline that permission request. In some cases, you may not need to ask for a permission. For example, you may be able to use the contacts picker instead of requesting the contacts permission. Another way in which we are updating our permissions model is to make it less abusable by bad apps. So take ransomware as an example. We've seen instances of this type of malware that take over your device and then demand payment before they let you back in. And they typically abuse two permissions. First, they use the system alert window permission to display an overlay on top of your entire screen so that you can't interact properly with your device. To address that, in Android O, we have changed the system alert window permission slightly so that app overlays can no longer cover up critical system windows. So they can no longer cover up the lock screen, they cannot cover up the status bar, and they cannot cover up the IME, as examples. Also, when there's an app overlay that's being shown, there will also be a notification that users can click on to hide that overlay window. Ransomware also take advantage of the device admin permission. They use it to prevent their own uninstall and they use it to change your passcode to lock you out of your device. Over the last few years, we have been continually de-scoping the device admin permission and replacing it with a less abusable alternative. In particular, in Android Nougat, bad apps can now no longer use the device admin permission to prevent their own uninstall, and they can't use it to change your passcode if you already have one set. To learn more, we actually have a talk one of our coworkers gave at a different conference, so check that out. Another way in which we've updated the permissions model in order to protect users is to take a stronger stance on privacy. Over the last few releases of Android, we've been steadily removing access to persistent device identifiers. So for example, in Android O, the Android ID property is now scoped per user and per app. The net.hostname property, which contains the network hostname of your device, is now empty. To learn more about the changes in Android O regarding persistent device identifiers, check out the blog post that's on the screen. That will tell you all the changes as well as some best practices. So everything I've talked about so far relates to installed apps. So what about instant apps? If you guys were here in the last session, actually in this tent, there was a session about instant apps. So instant apps, for those who don't know, is a feature coming to Android where you can click on a URL and open it immediately in an Android app, even if you don't have the app installed. So that has the potential to greatly improve user experience, as well as increase in apps' user engagement and conversion numbers. On the other hand, opening up arbitrary URLs in apps also comes with associated security and privacy risks. So how do we want to address that? We are addressing that by creating an updated permissions model that's really tailored to the capabilities and characteristics of an Android instant app. In particular, instant apps will have security and privacy best practices baked in. For example, instant apps must use runtime permissions. And instant apps will use HTTPS instead of HTTP by default. There are a lot of Android permissions that instant apps actually cannot access. They cannot access any persistent device identifiers. And another example is that they can't access the contacts permission. You must use the contacts picker instead. As app developers, if you make your normal app deployable as an instant app, it actually makes your normal app much better, too, because you're now automatically using security and privacy best practices. And for users, if the majority of your apps are now using these best practices, then your device becomes a little bit safer, too. So we're very excited about the instant apps model. So while permissions is really a way to control app access to data, within the operating system itself, we sandbox and isolate every process and every app to limit the ways in which a compromise in one can affect the others. For many years in Android, we have been steadily improving the application sandbox enforced with SE Linux. And we'll see how that's doing in the next slide. In Android Nougat, we applied these same sandboxing principles to the media server to significantly harden it. And now in Android O, with Project Treble, we are taking isolation to the next level by putting device-specific vendor components into their own sandboxes. So how are we doing there? We looked into the data, into the Android Security Bulletin data from the first 4 months of this year. We looked at all the kernel bugs, and we see that about half of the kernel bugs, almost half, SE Linux actually reduced the severity of almost half of those kernel bugs by making parts of the kernel unreachable by untrusted apps. We made it so that it's much harder to exploit those parts of the kernel. And that's what SE Linux really helps with. As I mentioned earlier, we took the same sandboxing and isolation techniques and applied it to the media server. In older versions of Android, the media server used to be this one giant, monolithic, very complex process that had access to a lot of permissions. In Android N, we broke that up into 6 different processes and put them into individual sandboxes with much tighter permissions, so that a compromise to any one of them only grants access to a small subset of the permissions and not the permissions of the entire media server. We also integrated integer overflow sanitization into the media server, where we're able to detect memory corruption that results from integer overflows. This helped us find a lot more bugs earlier in the development process and limited the severity of any bugs that occur at runtime. So how did we do there? We looked into the bugs, the Android Security Bulletin bugs from the first 4 months of this year. And we see that of all media stack bugs that affected Android Marshmallow, more than 20% of them, actually, are no longer security issues in Android N. And a few more bugs on top of that downgraded in severity from Marshmallow to N. And we're not done yet. So in Android O, we took sandboxing and isolation to a whole new level with Project Treble. With Project Treble, we're putting the Android OS framework and the vendor implementation, the device-specific vendor implementation, into different processes that communicate with each other using a standard vendor interface. This vendor interface will be maintained from version to version, which means a newer Android OS framework will run with minimal changes on top of an older device. And that paves the way then for us to release new Android OS framework versions with shiny new features and new security enhancements, and have it be adopted much more quickly by the entire ecosystem. So that's very, very exciting for security. Also, the vendor interface allows us to enforce a boundary between the framework and the vendor implementation so that we can use it to limit the ways in which a bug in one can affect the other. To take an example, let's go back to the media server. As part of Project Treble, we have re-architected the media server again in Android O and taken the audio, camera, and DRM hardware abstraction layers and put them into different processes and different sandboxes. What that lets us do is to say the framework pieces actually now no longer need access to the kernel components, the kernel drivers that control media playback. And so now we can put the framework pieces also into tighter sandboxes as well, and make it so that an exploit in the kernel, a compromise in the kernel, it's now much harder for that compromise to exploit certain areas of the it's now harder for compromises in the framework to exploit certain areas of the kernel. All right, so speaking of the kernel, why is the kernel important? In the last year, we have spent a lot of time hardening the kernel. And we did that for one major reason. We see that kernel bugs are becoming a much larger proportion of Android security bugs. Whereas in 2014, about 4% of Android security bugs were kernel bugs. That number increased significantly to about 44%. And there are probably a couple of reasons for this. One is we've made a lot of progress in hardening the user space. So for example, the application sandbox that's enforced by SE Linux, that's gotten a lot better over time. And in order to break out of that application sandbox, in order to break out of the SE Linux sandbox, you have to compromise the kernel. Also, the kernel is very powerful, has a large attack surface. It's kind of like the king piece in a game of chess. You take the kernel and you win the game. And so we decided to spend a lot more time thinking about how to harden the kernel. So we looked into what causes kernel bugs. We looked into the data from 2014 and 2016 and categorized different kernel bugs into different categories. And we see that the largest category, accounting for about 45%, is this missing and incorrect bounds check when we're copying data from user space to the kernel. So we presented this exact same data to the Linux upstream community and to ARM last year. And to their credit, they were super responsive. Within a couple of months, they gave us a feature called hardened user copy that addresses this entire category of kernel bugs. So we have since then backported hardened user copy to the Android kernels 3.18 and above. And we have also implemented a few more security features on top of that. We have implemented PAN emulation. We have implemented KASLR, and many others. So all of these kernel features taken together, we expect that they will have a huge impact on the number and severity of kernel bugs in the future. Another way in which we are protecting the kernel is to reduce its attack surface. We're using a technology called seccomp to enforce a whitelist of system calls that apps can use to communicate with the kernel. Any system calls that are not on that whitelist will be blocked by the seccomp filter. So everything that's on the whitelist, that includes system calls that are made by all public libraries that are supported in Android. So, and we have tested many of the top apps as well as Google apps. So we expect that this actually won't impact almost any app. But if you do have an app that uses a lot of native code, we do encourage you to test that app on an Android O device to make sure that any system calls that you make are not affected by the new seccomp filter. Having this whitelist of kernel interfaces allows us to really focus and concentrate our testing and quality assurance efforts on this well-defined whitelist, and also be more confident that the rest of the kernel is protected and that it's much harder to exploit the rest of the kernel. Seccomp is actually not new to Android. Chrome has been using it for quite a while, in fact. So Chrome has their own app-defined seccomp filter around their renderer process. They use this seccomp filter to make a few guarantees. They want to guarantee that the renderer process can read global state, but it cannot modify a global state. And in fact, this has been quite useful in quite a few times. Recently, we've seen a few kernel bugs that were actually unreachable from the Chrome renderer process because the relevant system calls were blocked by seccomp. OK, so that was a really quick overview of the updates, of the security-relevant updates in the Android OS. Let's now turn to app security. In particular, we'll talk about a couple of features that improve the security of your apps. First, let's go over WebView. So WebView has been with Android since the very beginning. It shipped up until KitKat, it shipped with the operating system, which means that if there were any bugs in WebView, it actually was not very easy for us to fix those bugs and get them out to users quickly. We addressed that with Android Lollipop when we made WebView a separate APK that is updatable every 6 weeks by the Play Store. And now with Android O, we've added quite a bit more, a few more security features to WebView. In particular, the WebView renderer process, similar to how it works on Chrome, now runs as an isolated process separate from the rest of your app. This means that any crashes or any compromises to the renderer process no longer really affects your app. And any website that is able to exploit the WebView process can't easily use that to exploit the rest of your app. The renderer process, in fact, is put into a very, very tight sandbox using seccomp and other technologies. For example, it cannot write to the network on its own, talk to the network on its own, or write to disk on its own. And so that also protects the rest of the operating system from any exploits in WebView in the renderer process. Another cool feature coming to WebView is safe browsing. So safe browsing has been available on Chrome for quite a long time. When users visit a website that's known to be malicious, safe browsing will show a warning and prompt the user before continuing. Safe browsing has been showing useful warnings to users more than 250 million times per month. And now it's coming to WebView on Android. Safe browsing is actually implemented within the WebView APK that's updatable every 6 weeks via the Play Store. And so you can actually change your app and protect your users almost immediately. Another important aspect of app security is device and user authentication. So why is device authentication important? Well, if you're using your phone to buy things or to unlock your home door, you want to make sure that no one can pretend to be your phone. And so what you can do is you can use the Android Key Store APIs to generate a key pair to uniquely identify your device. The benefit of using the key store APIs is that on new Android devices, key store keys are protected by secure hardware, such as the trusted execution environment. And so even in the event of a kernel compromise, no one can extract out those keys and clone them onto another device. There was always one question remaining, though, which is, how do you actually know that those keys are properly protected? Let's say you're on the server side. How does your server verify that you're talking to a device that's using keys that are properly protected by secure hardware? This is where key attestation comes in. With Android O, we're adding in an attestation API for compatible devices, where at a high level, your server can talk directly to the secure hardware, the trusted execution environment on the device, and ask it to give you signed assertions about the properties of the keys that it protects, as well as about the properties of the device. So for example, the key attestation API can tell you whether the key itself actually is protected by the secure hardware. It can also tell you, for example, whether verified boot passed on that particular device. The associated attestation certificate chain on compatible devices is actually rooted in a Google certificate. So that's how you know that that device itself is known to Google and is compatible with Google standards. All right, so that was device authentication. So what about user authentication? We're happy to let everyone know that with the next version of Google Play services, we're also adding APIs to support FIDO U2F security keys. As you probably know, security keys are second-factor tokens that are already accepted by many major websites such as Google, Facebook, GitHub. And security keys, as compared to traditional second-factor methods, are faster to authenticate and harder to phish. So we know that for a lot of users, one of the most important things that they can do to secure their user account is to enable second-factor authentication. So we're very excited that security key support is coming to Android. So to wrap up, we covered a lot of material. We talked about all kinds of improvements in the operating system. We talked about app security. If you want to learn more about making your app more secure, check out these developer resources. We have a checklist as well as some best practices. We also have a couple of code labs here at I/O that you can try out at the kiosks or you can try out online. So thank you for your attention. And if you have questions or any comments, feel free to email us at security@android.com, and we'll also be backstage. Thank you.